I've previously gone over Chapter 11, Section 1, which was simple harmonic motion. Now we're moving on to Chapter 11.2, which is measuring simple harmonic motion. In this section, we're going to start to look at waves, and in order to do so, I'm going to define some basic terms that will help us to study these waves. So the amplitude is defined as the maximum displacement from equilibrium position. I'll refer to this in the future probably as A. So the amplitude would be this distance. You may recognize this from math if you've had sine or cosine waves before. The amplitude is simply this distance from the equilibrium point to the farthest point away. The period is the time it takes for a complete cycle to occur. So a complete cycle for this wave would be from this point to this point. That's where the wave completes one full pattern of sort of this S shape before repeating and forming more S shapes later on. Whatever time it takes for this to occur is expressed as t, that's the period. Finally, the frequency, which is written as f, lowercase f, is the number of cycles per unit of time. So this is the inverse of period, which we also call 1 over t. And frequency is expressed with the unit hertz, which is written as Hz. So that'll be used later on as well. Going back to the simple pendulum we discussed in Chapter 11.1, I'm going to give you an equation for the period of a pendulum. This depends on the length of the pendulum and the free fall acceleration, and it's simply the time that it takes for the period to complete one complete cycle. And these are different factors than the factors that influence the period of a mass on a spring, which we'll get to later. So we write the period of a pendulum as t, or period, equals 2 pi root L over g, where L is the length of the pendulum from the top to the bob, so it's this length, and g is gravitational acceleration, which we know to be about 9.81 meters per second squared. So when we're applying this equation, you can visualize that as the length of the pendulum increases, its period would also become larger because it has a longer arc to travel through. If I draw two pendulums where one is very short and one is longer, and you visualize these pendulums swinging back and forth over the same angle, the longer pendulum at the bottom would have a much longer arc to travel through than the smaller one. You may also wonder why factors such as the release angle are irrelevant when we're measuring the period of the pendulum. Well, it's somewhat irrelevant over small angles because the initial acceleration is greater if you release the pendulum from a bigger angle, and that will cancel out the fact that a pendulum released from a bigger angle has a longer distance to travel through. The equation for the period of a spring looks somewhat similar to that of the pendulum. However, it depends on slightly different factors. In this case, we write that the period, t, is equal to 2 pi root m over k, rather than L over g. So this m is just the mass of whatever block or object you have on the end of the spring mass, and k is the spring constant. This equation is also pretty logical because you can visualize that a mass that's larger will take longer to complete the same cycle because force is mass times acceleration, and as the mass increases with a constant force, the acceleration would have to decrease, making it take longer. The period of the mass on a spring is inversely proportional to k, or the spring constant, because as that increases, the spring will exert a greater force on the mass, making the period shorter and the motion faster. So here are some practice problems for section 11.2. Number 1. You are designing a pendulum to have a period of 1 second. How long should the pendulum be? So we know that pendulum period depends on length, so I'll write out our equation where period is equal to 2 pi root L over g. Now we're ready to plug in some variables and solve. So we know that we want the period to be 1 second. That will be equal to 2 pi root L is what we're solving for, and then g we'll call 10, just to make it a little bit more simple. Now to isolate the L, I'm going to divide both sides by 2 pi, and I get that 0.16 is equal to L over 10, and that's still the square root, sorry about that. So then I'll square both sides to get rid of that square root, and I'm left with 0.025 equals L over 10. Now just by multiplying this 10 over to the other side, I get that L is equal to 0.25 meters, or in other words, L equals 25 centimeters. That would be the length of the pendulum. Practice number 2. Calculate the period of a 3.5 meter pendulum in the following locations. A, the North Pole, where G is equal to about 9.832 meters per second squared. Okay, so in this case, they're changing the variable of free fall acceleration, or G, which is slightly different at different locations on Earth. And we're solving for the period. So we have our same equation where T is equal to 2 pi root L over G. So for the North Pole, T equals 2 pi times the square root of 3.5, that's the length of the pendulum, over 9.832. That's the value of G. Now if I plug in all these values and solve, I get that the period is about 3.75 seconds. That's how long it takes for the pendulum to complete one cycle. Now they're asking for Indonesia, which is closer to the equator. In Indonesia, G is about 9.782 meters per second squared. So again, I'm going to be solving for period, so I'll do 2 pi root L over G. T equals 2 pi, and then I'll plug in my variables where L is still 3.5 and G is 9.782 meters per second squared. If I simplify and solve this, there's not actually much of a difference. I get 3.76 seconds. So that's how long it would take for the same pendulum to complete a cycle in Indonesia. Number 3. A mass of 0.3 kilograms is attached to a spring and set into a vibration with a period of 0.24 seconds. What is the spring constant? So now we're looking at a situation with a spring, which means that we'll be using a slightly different equation for its period, where T equals 2 pi times the square root of m over k, or mass over spring constant. Now we can plug in all the variables they've given us. The period is equal to 0.24 seconds. Then we have 2 pi root 0.3 over, and then k is what we're solving for. So I'll divide both sides by 2 pi, and I find that 0.04 is equal to the square root of 0.3 over k. Then I'll square both sides to get rid of the square root sign, and I'm left with 0.001 equals 0.3 over k. If I multiply the k over here, I would have 0.001k equals 0.3, so then I'll divide both sides by 0.001 to isolate the k. I get that k is equal to about 205.6 newtons per meter, and that's the spring constant for this spring. Finally, we have number 4. A 0.75 kilogram mass is attached to a vertical spring and stretches at 0.3 meters. A, what is the spring constant? Okay, so we know that k is measured in newtons per meter. We know that the spring was stretched by a 0.75 kilogram mass. That would be 7.5 newtons. And then meters, we have 0.3. That's how far it stretches. Now I'm dividing, and I get that the spring constant is about 25 newtons per meter. In part B, it says that the system is now placed on a horizontal surface and set vibrating. So basically, if you can visualize this, the spring is now placed like this, and the mass is allowed to oscillate back and forth. It's asking what is the period. So T is equal to 2 pi times the square root of m over k, and we solve for all these variables now, so I can plug in 2 pi square root of 0.75, which is the mass, divided by 25, which I just solved for in part A, that's the k value. And then by simplifying, I get that the period is equal to 1.1 seconds.